So, good morning, a very good morning to all of you. I hope you can all see my screen and hear me clearly. In this class, we are going to do some of the problems in rotation. So, you can sit with your pen and paper and try to write down some of the problems, solutions, some pointers here and there. So, my first problem is here. The angular position of a 0.36 meter diameter flywheel is given by theta is equal to 2t cube. Find its angular position as t1 is equal to 2 seconds and t2 is equal to 5 seconds. Find the distance that a particle on the flywheel rim moves over the time interval from t1 equal to 2 seconds to t2 equal to 5 seconds. Find the average angular velocity in that interval. Find instantaneous angular velocity at 2 seconds. Find the average angular acceleration between that interval and find instantaneous angular acceleration at 2 seconds. So you can see that there are a lot of small things to be calculated, and this is a problem on rotational kinematics. So we have been given theta, the angular displacement, as a function of time. Since theta is known to us as a function of time, I can substitute suitable time value and get my answers for theta. So in place of t, I will substitute 2 here, and I will get my answer is 16 radian. How do you convert into degrees? So you all know 1 radian, or you all know that it's 2 pi radian is equivalent to 360 degrees. So in fact, take 16 radian, multiply by 360 and divide by 2 pi. You get 920 radians. So 16 radians multiplied by 360 by 2 pi will give you 920 degrees. Sorry, not in radians. Next theta is at 5 seconds, so it will come out to be 250 radians or 14,000 degrees. So you have to find delta theta, find the distance that the particle on the flywheel rim moves over the time interval from 2 to 5. So for that I will need delta theta. So this minus this, take this value, subtract it from 250, you get 234. Now the linear displacement is r times delta theta. R is 0.18 into 234, that will give me 42 meter. The next is the average angular velocity in that interval. Average angular velocity we have seen is delta theta by delta t, which is 234 by 3, which is 78 radian per second. Now next is instantaneous angular velocity. So to find the instantaneous angular velocity, you will take the derivative of theta equation. Theta is 2t cube its derivative will be 6t square. So omega is d theta by dt at 6t square. You are supposed to calculate omega at t is equal to 2 seconds. So it is here. Put the values, you get 24 radian per second. Now once you get 24 radian per second, I can calculate omega at t is equal to 5, which is 150 radian per second, and that can give me the average acceleration between that interval. So the average acceleration is change in omega upon change in time. So 150 minus 24 is 126 divided by time interval 5 minus 2, which is 3. That should give you 42 radian per second square. Note down the unit. It was radian earlier for displacement, radian per second for velocity, radian per second square for angular acceleration. How do you get instantaneous angular acceleration? The last thing. So you take omega equation as 6t square and take its derivative. So its derivative will give you 12t. So at t is equal to 2 seconds, you get 24 radian per second square. The next is a Blu-ray disc's angular speed is 27.5 radian per second at t is equal to 0. Its angular acceleration is minus 10 radian per second square. What is the disk's angular velocity at t is equal to 0.3 seconds? What will be the angular displacement? You know, the Blu-ray DVD or Blu-ray disc are they were the advanced form of CD or compact disc devices before 4G came. With the advent of 4Gs, the importance of DVDs diminishes. I think with the advent of 5G, the Blu-ray or whatever DVDs are there, they will be completely out of picture. So this is a problem which is based on that. So I have written my data which is given. Initial angular velocity is 27.5 radian per second. Initial angular displacement theta 0 is 0. Total time in which I have to make my calculation is 0.3. Angular acceleration is minus 10 radian per second square. So all the data which is given I have noted down. That is one of the standard way to solve physics problem. You first write down all the data which is given in the problem in proper units, and if any conversion is needed, then do that conversion right here. Then I can find the angular velocity. We can use a kinematical equation for rotational motion. We have done it in theory. Omega is equal to omega 0 plus alpha t. So omega 0 is 27.5, alpha is minus 10, t is 0.3. You put the value, you will get your answer. An angular displacement, theta is equal to theta 0 plus omega 0 t plus half alpha t square. Omega 0 I can take as 0. Whatever initial point it started, or whenever the observation started, I will call that angle, that angular position as my reference position and declare that theta 0 is 0. So the only thing that remains is here. So put these values, 27.5, t is 0.3, alpha is minus 10, t is 0.3 again, solve it, you get 7.8 radians. Sometimes it might be asked that how many revolutions it has finished in that particular angular displacement. So you can see that in one revolution, a rotating body finishes 2 pi radian of rotation. So in 7.8 radian of rotation, it will be 7.8 multiplied by 1 upon 2 pi, and that will give you 1.24 revolutions. So this is the second conversion that I am discussing with you people today's class. So this is our problem on moment of inertia. I will try to cover all the, or at least most of the topics when I am taking problems on rotation. A machine part consists of three discs linked by lightweight struts. So these rods are lightweight, you can ignore the weights of the rod. Discs are heavy. What is the body's moment of inertia about an axis passing through the center of disc A perpendicular to the plane of the diagram? So my disc is, the axis is passing through this point and it is perpendicular to the plane of the diagram. So I assume that these discs are very small and the entire mass is concentrated almost at a point. That is a very important assumption I am making. If I take these discs as too large, then I'll have to calculate the moment of inertia of each disc separately, which I'm ignoring. So the moment of inertia about the point A, now since this disc is lying straight away on the axis of rotation, the moment of inertia of this disc will be 0. So that will not come for the involved into calculation. It will have negligible moment of inertia compared to these two. So I can ignore it. So it is the moment of inertia of disk B about this axis and moment of inertia of disk C about this axis. Remember, the axis is perpendicular to the plane of the screen. So this to rotate, say, this way. So the radial distance for B is 0.5. So when you write mr square, you will write 0.10 into 0.5 square. And for C, radial distance is 0.4. So for C, you write 0.20 into 0.4 square. If you add up the two, you get 0.057 kg meter square. So this is your answer for the A part. What is its moment of inertia about an axis through the center of discs B and C? So the other axis passes through the center of B and C, that is along this axis. So what will be the moment of inertia then? You will find that same logic will apply since B and C are on the axis. Their own moment of inertia will be neglected, it will be 0. And you will consider only the moment of inertia of A, which is at a distance of 0.4 meter here. So mr square will involve only one term and it will be 0.048 kg meter square. What is the body's kinetic energy if it rotates about the axis through A with the angular speed of 4 radian per second? So kinetic energy is half Ia omega square. Ia we have already calculated 0.057. I can put it here, put my omega value, take the square, and I can calculate my kinetic energy as 0.46 joule. So that's a very straightforward problem. Many of you must have done it in your lower classes. As I said, we are revising the course. We will go through it. With that will be 234 radians. Okay, you mean to say that is there any correction here? 34. I think you're talking in this problem. No. Oh, there is some confusion with. Yeah, so what we have used is 234 here. So I guess that is correct. Okay. What is the torque acting in the wrench? So diagram is given to you. That's a straightforward diagram. So now this distance is zero point 0.8 meter, which is my R distance. R is zero point 0.8 meter. It's not lever arm, remember. Lever arm is the perpendicular distance between the line of action of force and the point about which the torque is calculated. So this distance will be lever arm. Zero point 0.8 meter is not lever arm, it is R. This angle theta is 19 degree. So I need to figure out what is this distance. So, so one way to do it very easily is that if you have seen enough or if you have practiced enough problems, then you will realize that this distance will be nothing but 0.80 cos 19, and that will solve the problem. But I'm going to the way which I have used to describe the theory. So if I used strictly that way, then I have told you that vector tau is equal to vector r cross vector f, or magnitude of torque is rf sine theta, but or theta prime. Remember, in this we have to look at the angle between r and f. Now 19 is not the angle between r and f. If you observe carefully, if this is r vector, then r vector will point in this direction, while f vector will point in this direction. So the angle between r and f is this angle, which a plane geometry will tell you that it is 109 degrees. So if this is 19 and if you drop a perpendicular, then this inner angle is 71 and this angle is 109. I call this angle as theta prime, and this is the angle between direction of r and direction of f. So when I expand this, it will become rf sine theta prime. So now you can put the values zero point 0.8 here, 900 and sine 109. That should give you 680 Newton meter. So that's how it will work. The other way to do it, if you want to find the lever arm from here to here, then you can use cos 19 as well. There's one more way to do it is that, and that was to find the component of f which is perpendicular to this line, perpendicular to r and parallel to r. That I would leave you people to explore. My next problem is a light cable is wrapped around a solid cylinder with mass m and radius r. The cylinder rotates with negligible friction about a stationary horizontal axis. The free end, so here is my diagrammatic representation. This is a cylinder, radius r, mass m. On that we have wrapped a cable which is massless. Finally, the free end of the cable, another mass m is attached. It is released from the rest at a distance h above the floor. So this is distance h above the floor where you are going to release it. As the block falls, the cable unwinds without stretching or slipping. Find the expressions for the speed of the falling block and the angular speed of the cylinder as the block strikes the floor. So here is my next situation. When the block strikes the floor, it will gain kinetic energy and velocity will increase, while the cylinder will set into rotation with some angular velocity omega. So what principle do we use to solve this? What concept, what idea, what basic principle? So you can see the basic principle that we can use here is conservation of total mechanical energy. There are no other forces working. So initially everything is at rest, so kinetic energy is zero. I can take this as my reference level. So potential energy of small m will be mgh. In this process, before and after, potential energy of capital M will not change. It remains at the same height, capital M, cylinder. So it does not matter. So we don't take that into consideration. Remember, if by any chance cylinder goes up or down, then we need to take that potential energy also in consideration. So this is my initial situation. My final situation is when it is hitting the around about to hit the block, then this block is moving. When it is about to hit the ground, this block is moving. Cylinder is moving, so they both will possess kinetic energy. This will possess linear kinetic energy, half mv square. Cylinder will possess rotational kinetic energy, half I omega square. As the block hits the ground, it reaches to the reference level. So its potential energy will be zero. So I can apply law of conservation of mechanical energy. So K1 plus U1 is equal to K2 plus U2. And then put the values 0, mgh is U1, K2 is these two terms, U2 is 0. Now in this, we are using disk here. So moment of inertia of disk is half mr square. So in moment of inertia, we can write half mr square in place of I, and in place of omega, we can write V by R. Remember, there is no slipping, there is no stretching. So in place of omega, we can write V by R. And then when you solve, you get the linear velocity of root 2 gh upon 1 plus capital M by 2m. And if you want to find out omega, then it is V upon R, where R is the radius. So these two parts are straightforward. The key idea is realizing that the conservation of total energy will give you the answer. And in total kinetic energy, you have to introduce the rotational kinetic energy. Good morning, Vijay. Nice to see you joining the lecture. In previous example, what are the accelerations of the falling block and tension in the cable? Now to find out acceleration of the falling block and the tension in the cable, we need to take care of Newton's second law in case of rotational motion. Now remember, in theory I had told you that to apply to apply Newton's second law to rotating bodies, we have to apply the Newton's law in both the forms, that is in the linear form, which is sigma f is equal to ma, and rotational form, which is sigma tau is equal to I alpha, simultaneously. So we need to apply the Newton's second law in both the forms simultaneously. So we will find out all the torques on the body and all the forces on the body, or on the system rather. Now on the cylinder, mg works downward at the center, normal reaction works upward from the axle, and they both will cancel or should cancel each other, as the block is neither, or as the cylinder is neither getting accelerated upward nor it is getting accelerated downward. So N and Mg must cancel. Also, they are acting at the center of mass of the cylinder. They will not apply any torque about the center of mass. But about the center of mass, the tension in the cable is working at a distance r. Lever arm is r for tension in the cable, and that will provide an anti-clockwise torque T into R. On the block which is falling down, tension works upward, mg works downward. The linear acceleration works downward. Remember, the cylinder will have something called as angular acceleration. Its angular speed will go on increasing. So let us see how do we write our equations. This is my first equation. This is Newton's second law written for the translational motion. So remember, cylinder is not undergoing translational motion. So N and mg will cancel out, balance out. So the only part of the system where sigma Fy will work is the block. Mg is positive, lower side is taken as positive. So Mg plus T is working now in negative direction. Acceleration is downward, taken as positive. So both mg and may are positive, T negative. This is how you write your rotational counterpart of Newton's laws. So sigma tau is equal to RT is equal to I alpha. I can be written as half mr square for a cylinder. So this is into alpha. Now this is how the linear and rotational accelerations are related. The linear acceleration of block is same as the linear tangential acceleration of the cylinder. So Ay is equal to A tan, which is equal to R alpha. So these three are my important equation. Once you get these three, rest is straightforward. So all now I can do is I can write T. So I can take AZ, and in place of AZ I can replace AY upon R. So once I do that and I solve it, I get T is equal to half MAY, and then this T value I can use in this equation. And then I can take AY common. So AY is G upon 1 plus capital M by 2M. So I will keep this equation and I would try to find out the tension now. So go back and substitute in tension equation the value of AY. So I have substituted. And once you do one more step solution, you get mg upon 1 plus 2m by m. My next question, perhaps the last one. A bowling ball rolls without slipping down a ramp, which is inclined at an angle beta to the horizontal. So here is the ramp. Here is a big ball and it is rolling. Mass is capital M. What are the ball's acceleration and the magnitude of the friction force on the ball? Treat the ball as uniform solid sphere, ignoring the finger holes. So here is my force diagram. This is my ramp. I will take my x-axis parallel to the ramp. So it is also inclined at an angle beta. My y-axis is perpendicular to x-axis or perpendicular to the ramp surface. The normal reaction will act at the center of mass and it is working in along the positive y-axis. Mg will work in vertically downward direction. It will make an angle beta with the y-axis. Force is working at this point along the rim and it is working towards the backward direction. Just try to imagine if this force had not been there, then the sphere will start sliding instead of rolling. So if you keep objects on incline, they tend to slide. But if there is a friction and if this is a sphere, then it will roll. The friction will oppose the slide and it will work in the backward direction. So these are my forces. I can split mg into two components, mg cos beta and mg sin beta. So these are my two components. And from here I can see to it that F is working at a distance r from the center of mass. So again for this you can write two equations. One, a Newton's law for its linear part of the motion. It's moving on a straight line. So you can write a Newton's law as sigma F is equal to ma. And then you can calculate the torque of all the bodies, torque of all the forces, and calculate sigma tau is equal to I alpha. This is the direction in which it will start rotating. So let's go ahead and see how do we solve it. It's a sphere, solid sphere. So the moment of inertia can be written as 2 by 5 mr square. I can write my Newton's law for translational motion. So along this side, along x-axis, only force acting, sorry, there are two forces acting, mg sine beta in forward direction, friction in the backward direction, acceleration will be in the forward direction. So I can write mg sine beta positive, friction opposing it negative is equal to ma. So this side downward direction is taken as positive. So this is my sigma f equation. This is my sigma tau equation. Remember, normal reaction is considered working on the center of mass. So no torque due to that. Mg is working at center of mass, so no torque due to mg about the center. About center there is only one torque acting, and that is due to the friction, which is F into R, which is the lever arm. So Fr is equal to I alpha, put I value here. Also, the equation that will relate the linear acceleration and angular acceleration is A is equal to R alpha. So once I have written all my four equations, moment of inertia, Newton's law in translation, Newton's law in rotation, and this relating the angular quantity to linear quantity, I am in a position to solve this. So I can replace AZ by A. I will get F of R is equal to 2 by 5 MRA, and then I can use this into the sigma F equation and solve A as 5 by 7 G sine beta. Sorry, wait. So I can solve A centimeter, A center of mass. I can solve acceleration of the center of mass along x-axis as 5 by 7 G sine beta. Once you know this acceleration, you can put it back in this equation and you can find the force due to friction also. So you can do that as well. Video analysis of rolling body is an excellent project work as well. You just find the acceleration and then you can do various calculation. Acceleration can be found from tracker. But of course, right now, most of us have finished 1.01 projects. So let's focus on 1.02. So I will stop my lecture here. Thank you.